Start with the left. Okay. So what can we convert that into? What do you think?
If you manipulate the Pythagorean identity, you can get sine squared minus 1 equals negative cosine squared.
Yep.
So
Yep.
you could turn that negative cosine squared into sine squared minus 1.
So you're saying take this part of it and use the Pythagorean identity? Okay. So I'm going to leave the sine squared alone. This sine squared, I'm just going to rewrite sine squared of x minus, and then rather than cosine squared, so what you were saying, if you remember sine squared of x plus cosine squared of x, this is the Pythagorean identity, it equals 1. So if you take the sine squared and move it over here, you get 1 minus sine squared. Is that what you're saying?
No. So if
What were you
move
saying?
the 1 over to the left,
I'll move the 1 over. This over here.
so it becomes sine squared plus cosine squared minus 1. And then if you move cosine over to the right, it becomes sine squared minus 1 equals negative cosine squared.
Oh. I see what you're saying. Yeah. And that's totally fine. But let me erase this just so I can go along with my train of thought. And yours would work perfectly too. If we replace this cosine with 1 minus sine squared x, then we distribute that minus sign. Same result, yeah, just different way to do it. And that's the nice thing about these is there's tons of different ways you could potentially do these. So then if we distribute that minus sign, we get sine squared x minus 1 plus sine squared x. And we got 2 of those sine squared, so we would have 2 sine squared x minus 1. All right, I need some ideas here. Give me some ideas. Factor, which side?
The left.
Okay, because we notice if we look at the left side and the right side, they both have a common term, and that's kind of a useful skill to look at when we're trying to verify identities. It doesn't work on every identity, obviously, but it's quite common that you factor out a common factor. So if we factor out a cosecant squared, from that left side, if we factor out a cosecant squared, what are we left with?
1 minus,
So if I factor out a cosecant from itself, here you're left with the 1
minus cosine squared. Cosine squared.
minus cosine squared.
Oh, yeah. Is that the same thing as sine?
And then 1 minus cosine squared. We just saw this one on the problem previous. 1 minus cosine squared is a form of that Pythagorean identity, so we can change this into sine squared. So then we can change to cosecant squared of x times sine squared of x.
You can change cosecant to 1 over sine.
And then cosecant using the reciprocal identity. Cosecant is 1 over sine squared of x times sine squared of x. And then those factor each other out. And we get 1. All right. We always start with the left? No, we have on these problems just because, but you don't always have to start with the left. So we could start with the left. You were saying something about cotangent, so let me write this. Cotangent of x minus cosecant of x. What could we change that into?
Cosine over sine. Cosine over sine.
So cotangent is cosine of x. Okay.
Minus 1 over sine x.
And then change cosecant using the reciprocal identity. And then since I already have the same denominator, cosine x minus 1 over sine of x. Cool. Just curious, did anybody start with the right side? You started with the right side? How did that look? Let's do this. Or If we start with the right side, what could we do there?
Just cosine, it's just x over sine x and minus 1 over sine x.
Yeah, and I think I mentioned that a couple times. If you ever have a fraction with one single term in the denominator and multiple terms in the numerator, you can separate that into several fractions. So cosine x sine x minus 1 over sine x. And then, yep, just go backwards. So cosine over sine is cotangent, and 1 over sine is cosecant. Cool. Again, just going to get on my soapbox.
Find two things to plus or minus to make it a reference angle.
Exactly. If you didn't hear that suggestion, the goal is, and that's a great suggestion, the goal is to use either cosine of alpha plus beta or cosine of alpha minus beta, so that alpha and beta either add or subtract to 165, and alpha and beta are one of our special angles, like 45 degrees, 60 degrees, or a reference angle like 120 degrees, 150 degrees.
But it could be any of those, like if you wanted to do.
It could be any combination.
Okay.
Yeah.
Could you do alpha, where
Ooh.
you'd have 180 minus 165 is 15, so 30 degrees would be the reference angle, and then 1 over half of that.
Wait, say that one more time.
So we have 180 minus 165 is 15 degrees. 15 times 2 is 30 degrees, which
Oh.
is a reference angle, so we can do a half
Oh,
alpha
yeah.
30.
I hadn't thought of that when I wrote this problem, but yeah, that would work. Yeah. Can anybody think of? So that's fine. That way is not an issue. Just for the sake of staying with the learning target that was attached to this, let's try to figure out an alpha plus beta or an alpha minus beta that would equal 165.
5, 4, 5, 4, 2 by 3.
Okay. So you're in radians, all right. And radians is fine. But since we started in degrees, it might be easier just to keep it in degrees. But I'm not going to get. You're not going to get dock points for staying in radians. But somebody suggested 120 degrees. And why 120? What's the big deal about 120? It's one of our special angles on the unit circle. Its reference angle is 60. So that would work 120 plus 45. So what I would suggest doing on this problem then is considering, instead of cosine of 165, consider cosine of 120 plus 45. Now go to your reference sheet on the back and look at the sum or difference identities for cosine. And just imagine that one of these is alpha and the other one is beta.
So, you know how you have a plus or minus thing? So if it's plus, that means the.
Oh, I'm glad I meant to bring that up. Can I actually see your copy real quick? So on your reference sheet, the sum and difference formula is right here above your unit circle. Cosine, for example, you see where it says cosine alpha plus or minus beta? The plus is on the top and the minus is on the bottom. You see what I'm saying? If you look to the left and look at its identity, it's cosine alpha, cosine beta. Now which sign is on top?
The opposite.
Minus. So if you're going to do the cosine alpha plus beta identity, then it's cosine minus sine. That's just to save space. That's how they wrote these, just so they're not writing everything up. Did everybody understand that? So the identity itself doesn't include a plus and a minus. It's one or the other. It's alpha plus beta or alpha minus beta on those identities. I'm glad you asked. Thank you. We need the one where it says cosine alpha plus beta is equal to cosine alpha cosine beta. Now which one is it? Minus sine alpha sine beta. And what can I replace alpha and beta with in these? 120 and 45, exactly. So then this becomes cosine 120 cosine 45 minus sine 120 sine 45. Okay, what is cosine 120? Okay, cosine 45. Sine of 120. And sine of 45 is root 2 over 2. Okay, and from here on out, it's just, yeah, you can use a calculator. It does say, and you gotta be careful and read the directions, it says find the exact value. So your calculator can help you in some regard. If you type this into the calculator and hit enter, what do you think it's gonna give you? Decimal. Which you can use to check your answer. So once you simplify this, you can turn that into decimal, and then you check it on a calculator. But finding the exact solution is more than just relying on what your calculator is telling you from here. So these two terms multiplied together is negative square root of 2 over 4. And then these two terms multiplied together. What is the square root of 3 multiplied by the square root of 2? Square root of 6, yeah. Over 4. And then since these both have the same denominator, we can now combine this into one fraction. So negative root 2 minus root 6 all over 4. Wait, say that again?
Does it have to be negative square root?
Which negative?
Like, does it have to be in that order, or it could be like negative 6 minus the square root?
You can do negative 6, as long as you make the root 6 negative and the root 2 negative.
Okay.
Yeah. Yep. Okay, what questions do we have on this one? Yeah.
So my calculator gave me negative square root of 6 plus the square root of 2. How did we get to negative square roots? Is it just because negative times positive is a negative, and so it's make one negative? Or is it
Which negative are you asking about?
the final answer? Or is it just
What did your wait, your calculator didn't give you a decimal? You lucky.
But then it also gave me negative square root of 6 plus square root of 2.
In what form?
The exact form. Yeah, I did.
Let me take a look at it after. Take a look.
So when it's the exact value, this is the exact value.
Yeah, the one I've circled here is the exact value. Yep. Yep. Let's talk about potential differences, because again, if you understand this problem, that's awesome. But is this the exact problem that's going to be on the exam? No. If this changed to sine of 165, what would you have done differently? Would you use the exact same identity? You just change identities, right? So just be aware of that. And again, I want to make sure we're clear on how to read your reference sheet on those sum and difference identities. If it says sine alpha and then it has the plus or minus beta, you're only going to use one of the plus or the minus. Did I explain that clearly? Okay. And whatever one is on top, the plus is on the top, then it matches up with the plus or minus on the other side of that identity. Just make sure those match up. All right.
Oh, I have a question.
Yeah.
Would there be a tangent of sum of differences on the test? Because the tangent is a little bit different, how we have to effectively y.
Yeah, I would look at all three. Look at your homework and see what kind of homework problems we practice on those as well.
Be familiar with the tangent.
Yeah. I think question 5, the way I labeled question 5 on the title page, I think this is also from 3.2. So these are both from the same section. So now you need to look at your reference sheet for this identity, sine alpha plus beta. And if you read it correctly, it should tell you that it's sine alpha cosine beta. And then how does it continue? Plus, say again.
Cosine alpha
Oh,
Sine beta.
cosine alpha sine beta. And then you had a question about triangles?
Are they the same thing?
No, I would do different triangles because one triangle is going to have an angle of alpha and the other one is going to have an angle of beta.
Are they the same measurement triangles, or two different triangles?
I would do two different ones. So, for example, if we wanted to do a triangle, whoa, look at that. For alpha,
It's opposite over adjacent.
it's opposite over hypotenuse. So opposite here would be 1, and then the hypotenuse would be 2. Now, we kind of jumped a couple of steps ahead. Why are we even drawing a triangle related to angle alpha and then labeling that with 1 and 2? What are we even doing here? Because I didn't know what sine alpha is, so why am I trying to figure anything else out about alpha? Because I need cosine alpha, exactly. Looking ahead at this problem, I need cosine alpha, and they gave me cosine beta. They didn't give me cosine alpha. So I had to draw an alpha triangle using this information that sine alpha is 1/2. And then, we're going to need something here to figure out this adjacent side. Pythagorean theorem. So, yeah, we're going to have to use Pythagorean theorem. So 1 squared plus b squared equals 2 squared. So b squared equals 4 minus 1, which is 3. So b, this side here is the square root of 3. So then cosine alpha is equal to, now I'm going to write square root of 3 over 2, but now we need to consider where is alpha. It's telling us that alpha is in quadrant 4. So if you remember your quadrants, all students take calculus. Quadrant 4, cosine is positive, so I'm going to keep it positive root 3 over 2. Cosine alpha is root 3 over 2. Now we need another triangle for the beta angle. Well, that didn't work out. Needs to be a right triangle. There we go. We can put angle beta there. Now it's telling me that cosine beta is root 3 over 2. And if you remember, cosine definition is adjacent over hypotenuse. I'm looking at this ratio right here. Cosine is adjacent over hypotenuse. So the adjacent length would be here square root of 3. The hypotenuse would be 2. And now I got to find that opposite side because I need to find out what sine beta equals. Sine beta equals something. And, same triangle. It turns out to be one of our special angles, yeah. But if you didn't happen to recognize that straight up, you could still do Pythagorean theorem. You could say that a squared plus square root of 3 squared equals 2 squared. And then we have a squared plus 3 equals 4. Subtract 3 and we get a squared equals 1. So a equals 1. So now opposite angle beta would be 1 over 2. But where is angle beta?
3.
Quadrant 3. So we've got to make it negative 1/2. Because in quadrant 3, only the tangent and the cotangent are positive. So I believe we have all of the quantities we need. Remind me what sine alpha is. Sine alpha was given to us at the beginning of the problem. It was right here. Sine alpha is negative 1/2. So I can replace sine alpha with negative 1/2. Cosine beta
Is positive square root 3 over 2.
that was also given to us here at the beginning of the problem. Negative root 3 over 2.
Oh.
And then cosine alpha we had to figure out. Positive root 3 over 2. And sine beta, we figured out here, sine beta was negative 1/2. And then multiplying these together, Negative times the negative is positive. So we have positive root 3 over 4. Huh. Minus root 3 over 4. This is cool. So what's the exact answer? 0. Nice. If it had been plus, just for the sake of argument, let's say it was square root of 3 over 4 plus square root of 3. How do you add root 3 plus another root 3? Yeah, you'd have to do 2 root. So if you have a 1 root 3 and another root 3, how many root 3s do you have? 2 root 3. So you, anyway. If they were different terms underneath the square root, so let's say if it's square root of 2 plus the square root of 3. If they're different radicants, you can't add them together. But we got our exact answer here. We're good.
Can you switch from a positive to a negative when it came down to
Oh, this positive to that negative?
Yeah.
Yeah, it was because of that 1/2 right there. That negative 1/2 rather. What questions do we have? Not much really can change on a problem like this in terms of the procedure. The procedure is the same. Really, the only difference you can expect is it might be a different identity. It might be sine alpha minus beta or cosine alpha minus beta, but the procedure is the same on a problem like that. Okay? Right. Question 6 is from 3.3. We had some double and half angle identities in 3.3. Double and half angle. So first order of business might be to reference your reference sheet and figure out what the double angle identity is for sine. Sine 2 alpha is 2. Sine alpha, cosine alpha. Let's do an inventory of what we know and what we don't know. We know cosine alpha is negative 3/5, so I know cosine alpha. What about sine alpha? Yeah, we don't know it, so we're going to have to figure out a triangle like we did on the last problem. An alpha triangle. So if I make a right triangle and put alpha in one of its angles, and alpha would work anywhere in there except for the right angle, obviously. You don't want to put it for the 90-degree angle. I could have put alpha up here in the top. It would have been the same. Now, we've been given the cosine of alpha is negative 3/5, so that means the adjacent length is 5. The hypotenuse is, sorry, the adjacent length is 3, and the hypotenuse is 5. So if we did Pythagorean theorem, a squared plus b squared equals c squared, we would get a 4 right there. Yeah.
If it says between 90 and 180, is that quadrant? Or does a 2 count like that?
Yeah, this is quadrant 2. If you start at 90 degrees to 180 degrees is...
But the sine 2 a affect that? Would it still be in the same quadrant or would it change quadrants?
2 alpha might change quadrants, but this determination of sine and cosine of alpha, we can base it off of this information here. Where were we? Oh yeah. So the opposite length, there's 4. That tells us the sine of alpha is 4/5. Now maybe it's 4/5, but it could be negative 4/5. It depends on where alpha is. Alpha is in quadrant 2. So is it positive 4/5 or negative 4/5? Positive. Remember, sine is positive in the second quadrant. So I'm going to keep it positive 4/5. And from here, it's relatively painless because we now know what the sine of alpha equals. So we just need to replace this with 2. And then the sine of alpha is 4/5. Cosine alpha was negative 3/5. And then 2 times 4 is 8. 8 times negative 3 is negative 24. Negative 24 25ths.
We don't have to worry about it being in another quadrant with the 2 alpha.
Not for double angles. Where that comes into play more is our half angles. Because with that one, we have to decide, do we do the positive square root or the negative square root? Okay, now this one involved the double angle for sine. Take a look, just while we're at it, take a look at your reference sheet real quick for the cosine double angle. What if this had said find cosine 2 alpha instead of sine 2 alpha? Now obviously you would use a different identity, but take a look at the double angle for cosine. How many of them are there?
3.
Which one do you use?
Oh.
Any or all? They're all the same. I mean, they'd look different, obviously, but they would give you the same result. So you have a choice on cosine of 2 alpha. You can use any one of those 3. Okay. So half angles, these are also from 3.3. If you use your reference sheet, you'll find that the cosine of alpha over 2 has a plus or minus in front of it, and then a big old giant square root. And now I can't remember, is it the 1 plus cosine or 1 minus cosine? 1 plus. If you recall, if you were here in class during that 3.3 discussion, we don't use the positive and the negative. We've got to decide, is it going to be the positive or the negative? The way we decide is based off of where alpha over 2 is. So we know where alpha is. Alpha is between 180 and 270, but we need to figure out where alpha over 2 is. So if you divide everything, by 2, we get alpha over 2 is sandwiched between 90 and 135. So where is that? Where is 90 to 135? Which quadrant, I mean? Quadrant 2. And we're dealing with cosine. So remember, cosine in quadrant 2 is negative. So I want the negative part of this square root and not the positive. So I want negative square root of 1 plus cosine. And I used x, that should have been alpha, sorry. 1 plus cosine alpha over 2. But here's the nice thing, don't we already know what cosine alpha is? Yeah. Cosine alpha was given to us in the problem. It's negative 7/25. We just need to turn this into something decent looking. 25 over 25. 1 is 25 over 25. 25 minus 7 is 18. So this is 18/25. And then 18/25 divided by 2 is 18/50, which is 9/25. Ooh, this works out perfect. They're both perfect squares. How do you like that? Square root of 9 is 3, and the square root of 25 is 5, so this is negative 3/5. Now, I wouldn't count on this always working out so nicely. You may have numbers there that aren't perfect squares. Matter of fact, you probably will. So how would, let's just for the sake of argument, let me go back. What if it was, I don't know, the square root of 10 over 25? We could make that 2 over 5. I'm okay if you leave it like that, honestly. I mean, technical math book would separate this into 2 square roots, square root of 2 over square root of 5. And then, since this would make the universe implode, to leave a square root on the bottom of a fraction, they would multiply it by the square root of 5, and you get the square root of 10 over 5. That's going the extra mile. Anyway, I hope I didn't confuse you all. Negative 3/5. That's our answer. Now, we skipped 3.4. Just got rid of it completely. It was unimportant. We went right to 3.5. Ooh, inverse. What would be a useful tool in helping you evaluate inverse? The unit circle? Now, unit circle, yes, that's a useful tool, but there's still some things you need to know above and beyond. Where is, let's review this real quick. Where is the inverse sign defined on the unit circle? Which quadrants, I mean? The inverse sign is quadrants 1 and 4. Okay. The inverse cosine is quadrants 1 and 2. And then the inverse tangent is 1 and 4. Now, why is that important? Each one of those combinations gives us, let me back up. Each one of those combinations gives us a possible positive or a negative value to look for. If we're sine, we need to be in quadrants 1 and 4 because that's going to give us possible positive y values and negative y values. If we're for cosine inverse, we use quadrants 1 and 2 because that gives us possible positive x values and negative x values. And then same thing with tangent, 1 and 4. So if we're inverse cosine of a positive value, square root 3 over 2, between quadrants 1 and 2, where are the positive x values? Quadrant 1 on the right. On the left would be negative x values. So we need to find an x value in quadrant 1 that has positive square root 3 over 2. What angle matches up with that? Is it pi 6? Or is it 30 degrees? It says, though, it says in radians, so we better keep it radians. Now, that seemed like a pretty easy question, and it is. What if, I'm just thinking of variations. So let's talk variations here. What if, well, yeah, I mean, it could be sine inverse or tangent inverse. It could be different trig functions, but boy, there's not much that could vary here. What if it was, let me just write this one down. Inverse cosine of 7/2. What would we say to that one? It's undefined. No solution. Undefined is what we would technically say. Why is it undefined? Cosine inverse is defined between -1 and 1, right? So that one would be undefined. Go ahead.
When do you use the plus 2 pi k again? I forgot.
That's when we're solving equations. Yeah, when we're solving
Exact
equations.
value is just that, right?
If we're finding exact value and we're just evaluating an inverse, then it acts as a function. So that's a good question. If you remember from Monday, some of these, when we were evaluating, we had to put a plus 2 pi k. From section 3.5, when we're just evaluating inverse trig functions, they act as functions. One input, one output. One input, one output. All right, question 9, also from 3.5, a little bit different. The impulse here, I'm just going to be honest with you, the impulse that students have is, wait a minute, cosine and inverse cosine, those are inverse functions, so don't they just automatically cancel each other out every single time? And the answer is sometimes they do, sometimes they don't. They're only inverse cosine, or they're only inverse operations if what we're evaluating is within the defined parameters. For cosine, it's got to be in quadrants 1 or 2. 4 pi thirds is in quadrant 3. So these do not act as inverse operations, or inverse functions, rather. So what we need to do is evaluate the cosine of 4 pi thirds into a numerical value. What is the cosine of 4 pi thirds? Negative 1/2. So then we change this to negative 1/2.
You're right.
And now we can evaluate an inverse cosine using the unit circle. Where do we have an x value? Now let me ask you a question. I want you to look at the whole unit circle. Where do we have x values of the whole unit circle that's negative 1/2? Aren't there 2 places? But remember, cosine's quadrant 2 or quadrant 1. So, say again. Cosine of the x values. And it's only in quadrant 1 or 2, and the only place x is negative is in quadrant 2, so it's 2 pi thirds. Now, let's talk about variations. Suppose I erase the 4 and it's just inverse cosine of cosine pi thirds. Those they cancel straight out. How come?
Because pi thirds is within the domain of part cosine.
So in this case, they would just straight up cancel each other out, and the answer would be pi thirds. Okay. What else could be different? I mean, we could use different trigonometric functions, but the important thing that this problem is trying to help us realize is, I guess the question I started with, is inverse cosine always the going to cancel out a cosine? Is it always inverse? No, not always.
Yeah.
If you want to, can you just solve it out, even if it is just inverse cosine of cosine pi thirds?
Oh, like we did here?
Yeah.
Mm-hmm. Yeah. Go ahead.
So I thought that we could like cancel them straight out if the number, or I guess the radian after something. But it's really just if it fits into the quadrant or whatever.
It depends on what order. If it was cosine first and then cosine inverse inside, then this has to be between negative 1 and 1. Did you see how it's reversed here? How cosine? Is that what you were asking?
Yeah.
Yeah.
Okay.
Can it be like a cosine of a cosine of a cosine? You're really like getting into the section.
Yeah, that would be. You're getting into what do they call that down there at the very bottom? Limbo. You're getting into limbo down there. In that case, you just have to evaluate and then evaluate and then evaluate. Yeah. Okay, question 10. Also from 3.5. What do they? Let's see. What are they asking us to do here? Do these aren't inverses of each other, right? Sine inverse and tangent. So those aren't going to cancel each other out.
Would you just do like maybe try to do turn sine into like a degree angle, or you do pi fourths or whatever, and then just be tangent times pi fourths. Tangent pi fourths.
So, yep. So if you didn't hear the suggestion, what we need to do is just evaluate inverse sine. So inverse sine of square root of 2 over 2, we're looking for x or y values? Y values in quadrant 1 or 4. 1 because they're positive. So,
You did 10 over 5
yeah. So inverse sine of square root of 2 over 2, hopefully you've seen it on your unit circle, is pi fourths. Or, since they didn't really specify radians or degrees here, you could use degrees if you want. And then what is tangent of pi fourths?
Sine and cosine are the same value, so it's 1.
Yep, at pi fourths, because remember the tangent is y over x. But at pi fourths, y and x are the same. So something divided by itself is 1.
Woohoo!
We're getting there. These three problems, you know, this is what you can expect from 3.5. I don't want to move on quite yet. Is there any questions? 3.5 questions? Yeah.
This must be using random patterns and things, but if you were to take like the inverse function and put the normal function inside of it, then the rule of thumb would just equal half of what was already in the innermost function?
No.
Like, for example, on 9 you had inverse cosine, and then you had cosine 4 pi-thirds. What we came out with was 2 pi-thirds. So would that be a quick, very logical shortcut or no?
No. I mean, it's good that you're trying to find patterns because sometimes that's helpful in math, but the rule of thumb is if this angle is in quadrant 1 or 2, because we're dealing with cosine, quadrant 1 or 2, then inverse cosine and cosine cancel each other out. If it's beyond quadrants 1 or 2, so we could have done inverse cosine of, let's see, what did we have there? 4 pi-thirds?
Yeah.
So we could have done 5 pi-thirds. And where is 5 pi-thirds? Should be in quadrant 4, isn't it? So what is the cosine of 5 pi-thirds? So then we would do inverse cosine of 1/2. And then inverse cosine of 1/2. Pi-thirds. So that in that case it wasn't quite half. So in this cases you just evaluate this into a numerical value, and then you evaluate the inverse trig function of that numerical value to find the angle that. Does that answer your question? Okay. Right. Couple more and we're done. And if you didn't hear at the beginning, there are some bonus questions. There's 5 of them. What should you study for bonus questions? Graphing. Now I mean, there's a lot to it. What did we graph? We graphed sine, we graphed cosine, we graphed tangent, we graphed cotangent, we graphed secant, cosecant. So I would look at all of those. So there's 5 of them, or maybe there's 4. And there's a word problem. There's one word problem that's on as a bonus. So it's a word problem. So we've done 2 types. One of them is finding like the missing side of a triangle type problem or a spinning type one. So it could be either one of those. It does have words in it. I'll tell you that. I'll give you. The word problem has words in it. You have to read them. Okay. Okay. Solve the equation for solutions in the interval 0 to 2 pi. Suggestions.
Minus sin x on the right.
So are we just trying to solve for x?
We're trying to solve for x.
Sine.
That's a good way to start. Subtract sine x on both sides. We did a problem very similar to this on Monday.
And then just factor out sine.
And this is going to be a really useful tactic when solving trigonometric functions is factoring, looking for common factors you can factor out. In this case, we have a common factor of sine. So if I factor out a sine, that leaves me 2 sine squared x. There we go, minus 1. If you factor a term out from itself, you have to leave a 1 in its place.
And then would you factor even further and do like sin x minus 1 sin x?
You could. However, now we have a product. A product means 2 factors multiplying. I have this multiplied by this. A times b is equal to 0. This is essentially what we have here. So what does this mean about a and b?
And then you can factor further.
That means either one of them can be 0. So we got to solve for either one of them being 0. So sine x has to equal 0, and the other one has to equal 0. So sine x equals 0, or 2 sine squared x minus 1 equals 0. We got to solve both of those equations separately. And this really is no different than what you did back in 1050 when you were solving quadratic equations. When you had two factors that equal 0, you separated them, set them equal to 0, and solved it.
You basically just have extra stuff.
Say what?
You just basically have extra stuff.
Yep. Yep. What's the connection now between what we're doing and what we just did 3.5? Remember 3.5 was inverse trigonometry. Now we're solving equations. We have to use inverses now to get x by itself, because I know sine x equals 0, but what does x equal? Now we have to cancel sine using inverse trigonometry. So inverse sine. So x equals the inverse sine of 0. This is the connection between 3.5 and 3.6.
It's 0 and pi.
You list all of them? Oh, yeah, pi. Okay, so 0, pi, and 0.
So if you didn't hear what the question was, they say very specifically list all the solutions between 0 and 2 pi, including 0 and 2 pi. So where on the unit circle do you have y values of 0?
Pi and 2 pi.
And
Zero.
0. So on the unit circle you have 0 radians, pi radians, and 2 pi.
So we do include 2 pi?
Yeah, because it says less than or equal to right here.
I only asked because in the book.
Do they have less than or equal
I
to?
think it's probably less than.
Maybe they had less than there.
I would expect nothing less.
Nothing. Yeah.
Okay, so now do we factor out?
Wait, hold on. X equals 0. X equals pi. And technically 0 and 2 pi are the same. But no. These are the only three answers. We're done. We move on. Nope, we have some over here. Wait, this one looks a little more complicated. Add 1. Divide by 2, so we get sine squared of x equals 1/2. Square root both sides. So sine x equals, don't forget the plus or minus. And this is just something to keep in mind. Square root of 1/2. You're not going to find that on the unit circle. Square root of 1/2 is on the unit circle. But the square root of 1/2 is root 2 over 2. They're the same. And root 2 over 2 is on the unit circle. Did everybody follow that? If I square root both sides, I'm going to get the square root of 1/2. That's not on the unit circle, but you can change square root of 1/2 into root 2 over 2. And that is on the unit circle. So this actually has to split into two equations to solve. We need to solve sine x equals positive root 2 over 2. And we need to solve sine x equals a negative root 2 over 2. So where do we have x values? Sorry, where do we have y values on the unit circle of root 2 over 2? Pi fourths? 3 pi fourths. And the negative y values of root 2 over 2? 5 pi fourths, 7 pi fourths. Whew. So we had a few solutions to that problem. You will. You will remember it. Positive psychology. If you worry about what's not going to happen, then it's not going to happen. Look forward with anticipation of what will happen. Yes. Wise I am. What do we think about 12?
It's pretty complicated.
This one's it's, yeah. I didn't bring a book. Dang it. Yeah, if you'll rip out a piece of paper and write your names on it. This one's a little different. Okay, yes or no question. All three of these terms have a common factor, yes or no?
No.
So we can't do the exact same thing that we did in this problem because these both had a common factor of sine.
Can we replace cosine of x and do like 2x squared plus 3x plus 9?
Would you guys be able to factor this using just traditional factoring techniques? 2x squared plus 3x plus 1?
If you teach me how to factor, I forgot how to do those.
This,
Make sure you print your name on the roll.
yeah, yeah.
Just
Which
sign
way,
it.
this way? This way. Which way are we going? Why did I, because I forgot how to factor with the 2 in the front.
Do you guys see a connection between these two expressions?
Just X
Yeah,
and
you just do
cosine.
that.
All we do is take out cosine and replace it with this is substituting variables, kind of like what I showed you on Monday with that goofy, I think it was from 3.2 or 3.3, that problem that we tried to do that was really awful. So all this is a quadratic expression, or it's an expression that's called quadratic in form. So we can factor it using the exact techniques we would have used to factor this one. And if you've forgotten how to factor these quadratic expressions, it's worthwhile, I guess, to review it here real quick. 2x squared plus 3x plus 1 would factor into two parentheses like this. One of them would be 2x, the other one would be x.
Wait, can you refresh my memory about that?
One way you could do it, the traditional way of doing it, is you multiply the leading coefficient with the constant. So 2 times 1 is 2. Now we need factors of 2 that add to 3.
Oh, yeah.
So 1 and 2. So then what you do is you split that middle term up into these two values. So now you have 2x squared plus 1x plus 2x plus 1. Is this looking familiar? This is called factoring by grouping. You group the first two and the last two. What does this have in common?
X.
So if you factor out an x, you have 2x plus 1. What does this have in common? If there's nothing in common, you can always say that there's a 1 in common. So if I factor out a 1, then it doesn't change anything. So now I have x plus 1 and 2x plus 1. That's called factoring by grouping.
What happened to that extra X that you factored out?
It became part of this x plus 1 factor.
Oh, okay.
So if 2x squared plus 3x plus 1 factors into x plus 1 and 2x plus 1, how can we use that same technique for 2 cosine squared x plus 3 cosine x?
Replace cosine with X.
Just replace x with cosine x.
There you go.
So this would be 2 cosine x plus 1, and then the other factor would be cosine x plus 1 equals 0. It's using factoring in a little bit different way. Awesome way, I might add. So totally awesome. But since we're here now, we have the same situation. I have something times something that equals 0. So what does that mean about each of those two things? Set them both equal to 0. Just like the last problem. So I've got to solve 2 cosine x plus 1 equals 0. And cosine x plus 1 equals 0. Oh, mama. Cosine x equals -1/2 on that one. And over here, cosine x equals -1. So then we get rid of cosine by using inverse cosine. So inverse cosine of -1/2. Where on the unit circle do we have x values of -1/2? Say that again. 2 pi thirds. There should be one more spot with a -1/2 x value. 4 pi thirds. Where do we have an x value of -1? Just one spot on the unit circle. And that's x equals pi. How fun was that problem?
That was pretty cool.
The technique we used was just factoring. Yeah, it wasn't the same type of factoring as, so problem 11 was factoring out a common factor. This type of factoring is just called factoring a quadratic expression. So there will be a factoring type problem. You have two, so we've got 3 questions here from 3.6 on this practice test. There's 2 of them on the test. One of them is factoring. One of them is kind of like this one, number 13. We need to get to this one. Would you guys agree we spent a good amount of time talking about verifying identities?
Yes.
And beyond the fact that they're just super fun, what was the point of verifying that one side equaled the other side?
To confirm that it is true.
To confirm that it's true,
So that you can make the equation easier.
so you can make expressions easier, right? That really is the point of practicing verifying identities, is so you can make expressions easier. This expression, just by looking at it, is pretty gnarly. I wouldn't want to try to solve that. But if you recognize, wait a minute, this kind of looks like one of our identities, maybe.
It's like the two.
The alpha, the sine alpha.
It looks like the addition. Oh yeah, it looks
That way would work too. That.
two sine.
But if you imagine instead of the x's here and two x's, what if they were just alphas and betas? Then don't we have an identity that's sine alpha cosine beta plus cosine alpha sine beta?
What's sine plus alpha beta?
It's sine of alpha plus beta. That's the identity.
So now you just replace 2x.
And then alpha was really 2x, right? And beta was x. So then this becomes sine of 2x plus x, which is just sine 3x equals 0. So we've used the techniques that we have mastered from section 3.1, which we all love, to make a relatively difficult equation to start with turn into a, I'm not going to say easy, but it's easier. This is an easier equation to solve.
Would you then do the inverse of sine 3 of x and divide that?
So what are we solving for?
X.
X is inside of a sine function. That's no good. We can't solve for x if it's inside of a sine function. So we got to get rid of a sine function using inverse. So now I've got 3x equals the inverse sine of 0.
Yeah, 0.25.
So where is y values? Where are y values of 0 on your unit circle? So we're going to have to split this up. We have several places on the unit circle that have y values of 0, so we've got to set up 3x equal to all of those. So 3x, tell me one of them. 3x equals 0, 3x equals pi, and 3x equals 2 pi. Now, notice at the beginning of the problem, did it say between something and something? It did not. So this is one of these infinitely many solutions scenarios where it's an infinite number of times around the unit circle.
Do you really need to write with pi and 2 pi if it's equal anyway? Can you just write 0?
That's a good question. Let's finish dividing by 3 and see if that changes things. Because the question is, well, aren't 0 and 2 pi the same? Let's hold that thought for just a second. Okay, that's a great question. You would all agree, right, that we've got to divide by 3?
Yeah.
But what divides by 3 over here?
The 0 divided by 3.
0 divided by 3,
And then 2.
and the 2 pi k divided by 3. And for those that weren't here on Monday, what's the point of the 2 pi k expression? To show that we're going around the unit circle. 2 pi times 1 is 1 revolution. 2 pi times 2 is 2 revolutions, 3 revolutions. Because we're not constrained by 0 to 2 pi, we can have an infinite number of solutions here by just going around the unit circle. So, here it is. So x equals 0 over 3, which is just 0, and then 2 pi over 3, okay? And then x equals pi over 3 plus 2 pi over 3, okay? And then x equals 2 pi thirds plus yeah, this is not a like term with that because that has an extra factor there. Good question though. And that's it. That's a ton of stuff, you guys. Way to hang in there.
So is that the answer with all the plus signs?
Yep, the whole thing.
And what's the difference between a plus sign and like a comma, just a separate? Is it because like I have them together?
Yeah, because x equals, like for this one, for example, x equals pi thirds plus 2 pi 3 by changing the value of k from k equals 0 to 1 to 2 to 3 to 4.